Greetings fluid mechanics enthusiasts, Engineer Leonardo here. Well, on this video I'd like to talk about a little bit of the continuity equation, which is an important equation in fluid mechanics, in solving fluid mechanics problems, both analytically and numerically. So basically the continuity equation is a type of conservation equation. On this case, conservation of mass. People who will work more and are more familiarized with electromagnetism, electricity, and etc. They are, when you talk about a continuity equation with them, they usually associate with the continuity equation for charge. Okay. But here we will talk about the continuity equation for a fluid, right? So first of all, we start as an infinitesimal volume of fluid. Here, of course, we will apply the continuum hypothesis. So we are dealing above the molecular level, so we don't have to worry about that. And we will work with a cubic volume of fluid. Okay, so our infinitesimal volume, which is this V with a line here. So this V with a line here will be equal to delta X times delta Y times delta Z, okay? Its length in X direction is delta X, in Y direction it's delta Y, and in the Z direction it's delta Z, okay? Here I made simpler with Cartesian coordinates, but you can do this for other types of coordinates, but this is usually more straightforward. So we are dealing with a fluid which has a certain density, okay, which can vary in time. So the total mass in a certain time for a certain time t will be equal to ρ, which is the density of the fluid, times the infinitesimal volume here. Okay, so this will be also an infinitesimal mass. And the variation of this mass in time will be equal to the partial derivative of the density with respect to t times dx dy dz, okay? So what we're gonna do is take into account the possibility of the density variation in time plus the flux of mass, of fluid mass. In this case, it will be a mass discharge with units kilogram per second in the SI units in international system. So we have to assure that this variation of mass stays the same. So what we are saying that the mass, what the continuity equation says essentially is that the mass that goes in equals mass that goes out. Of course, here we are talking about mass of fluid. But this principle of conservation of mass is applicable most everywhere. Also, you can have a source of mass or a sink of mass on a certain volume of fluid, which we can also take for account on this equation, but we will not consider here any sources of mass. So first of all, we will compute the flux of fluid on the x direction, which will be on this direction. So here we have our flux, which conventionally it will be on the positive direction. This here we have the u component of velocity, which is the velocity on the x direction. So we have the discharge here on the x direction, and here the discharge plus the variation of this discharge here. Sorry, I'm getting used to this pen, this digitalizer table. So plus a first order approximation of the variation of this discharge. So how do we calculate this discharge here? So the discharge on the x direction will be equal to ρ times u, which is the velocity on the x direction, times the area which is the flow is occurring, which is dz dy. So it's ρ u dz dy dz, or dz dy. Okay, so the flow that goes in must equals the flow that goes out, right? So we have minus, because it's entering here, x qx plus qx plus variation of with respect to x dx, that must be equal to 0. Okay, so these terms here cancel out. Remember that we have this negative sign here because of the flux convention. So in every surface we have a vector which is normal to this surface, and we have to compute the scalar product, the dot product of this vector with this vector here. So that leaves us with the product of this unit vector here and here, times the cosine of the angle. Here the angle is 108 degrees, and here the angle is 0. Cosine of 108 degrees is -1, and here the cosine of 0 is 1. So the flux, the fluid flux, the discharge on the x direction is equal to qx dx, dqx dx times dx. Okay, so do not mess this derivative with this dx here. So now we have to substitute the discharge on the x direction, which is this expression here. Okay, so what we get is the whole u dx times dx dy dz equals 0. Okay, so now we have to do the same procedure for the y direction and the z direction, and account for variation of the density in time. Okay, so if you pay attention, this is actually equal to the infinitesimal volume that we are dealing with. Okay, So let me clean this. Okay. So what we get is here the x direction, dx, dy, dz, plus here on the y direction. Whole v dx dy dz plus on the z direction whole w dz, sorry, dx dy dz plus the variation and time of the density, which is here dx dy dz. This all must be equal to 0 in order to conserve mass. Okay, if we are not dealing with sources of mass. Of course, all this simplifies to the infinitesimal volume. Here and here, which can divide out this equation by this infinitesimal volume, considering that it's not 0, although it's very close to 0. And remember that our velocity vector is equal to u, v, and w. U is the velocity component on the x direction, v is in the y direction, and w on the z direction. Okay, so this equation here simplifies to this dx whole times plus the dy plus d dz, partial derivative, right? Okay, equals 0, and I'm gonna add this term here on the front. Okay, so this is the general form of the continuity equation, both for incompressible fluid, for fluids with varying density, and for incompressible flow we don't have a significant variation of the density, although we can have a variation of density in time for incompressible flow. But considering that the density is constant, and then the flow with regarding the density is steady, this equation simplifies to this. This term here will be equal to 0, right? Because it doesn't vary in time, it is constant. And because this density is constant, we can take it out of the derivative. So we get this. Here and here, dw dz equals 0. We can divide this equation by the density, and what we get is the continuity equation that most people are familiarized with. Okay, we can write this equation as the divergence of the velocity vector. So this is equal to it's terrible. Okay, it's nabla operator, the dot product of the velocity. Equals 0. That is usually called the incompressibility condition. Okay, and also we can write this as the div, the divergence of u equals 0, and also in its tensor form, which is ui dui dxy equals 0. Okay, so we have three forms here of writing the continuity equation in its for incompressible fluids. Okay, this equation can be applied for fluids with varying density such as stratified flows, using the Boulson-S approximation. If variation of density is of order of 4%, so if this term here is of order 4%, we can apply this equation here, the continuity equation, on its incompressible formulation. Okay, well, I hope you enjoyed this video. Don't forget to like, subscribe, and comment, and share this video with others. See you next time. Bye.